Okay, so before we are able to synthesize our fatty acids, we need to generate the precursors. So the precursors for fatty acid synthesis originate in the mitochondria, and they need to be transported into the cytoplasm. So recall the generation of pyruvate from glycolysis. And this pyruvate is being driven from the oxidation of glucose, and of course with the oxidation of glucose in liver, this is going to be the fed state in the liver. So the fed state means that we have high plasma glucose levels, plenty flowing in through GLUT2, generating a high amount of glycolysis, coming down to pyruvate. Now at this point, the pyruvate enters the mitochondria through our pyruvate proton transporter, and then the pyruvate is going to be converted into acetyl-CoA by the pyruvate dehydrogenase enzyme. The next step is acetyl-CoA will condense with oxaloacetate from the TCA cycle, and this is the entrance, of course, of the TCA cycle for acetyl-CoA. We are making citrate, then the citrate will be processed by a aconitase into isocitrate by the isocitrate dehydrogenase enzyme. Now at this point we have to consider the physiological state, which is the fed condition in the liver. So that means we have lots of oxidation of glucose, so our NADH levels are exceptionally high because of that oxidation of acetyl-CoA through the TCA cycle. This will essentially inhibit the next step of this reaction, which is the isocitrate dehydrogenase enzyme, to form alpha-ketoglutarate. Now if the dehydrogenase enzyme is inhibited, that means we're going to have a buildup of our isocitrate, and then that will of course drive the reaction in the reverse direction to reform citrate. Again, because we have a high NADH concentration to inhibit the dehydrogenase in the fed state in the liver. Once this happens, the citrate, of course, will now be able to exit the mitochondria, and this is going to use a transporter. Once the citrate is in the cytoplasm, we now are able to use our enzyme citrate lyase to break the citrate into acetyl-CoA and oxaloacetate. Now at this point, the acetyl-CoA has two directions. Recall from our last video, we can use this for cholesterol synthesis, or we can use this for fatty acid synthesis. Now before we talk about fatty acid synthesis from this cytoplasmic acetyl-CoA, let's talk about this oxaloacetate. This is potentially a dangerous reaction because we're taking oxaloacetate, a TCA cycle intermediate, out of the TCA cycle, out of the mitochondrial matrix, depositing it into the cytoplasm. It's dangerous because we're taking intermediates out of an important energy production pathway, which would deplete this, slowing down the TCA cycle. So that means we have to have a mechanism to return the oxaloacetate back to the mitochondria. So the way we're going to do that is we are going to convert the oxaloacetate into malate. This, of course, is done by the malate dehydrogenase enzyme. This is different than the one that is used in the TCA cycle, different locations. This one is in the cytoplasm. This, of course, is a redox reaction. So we are going to use NADH in this case to reduce oxaloacetate into malate. So we're oxidizing NADH into NAD. Now recall this NADH is coming from glycolysis, which is the conversion of glyceraldehyde, 3-phosphate, to 1,3-bisphosphoglycerate. This reaction, of course, will require the input of inorganic phosphate, and for our purposes here, most important is we are generating NADH, energy molecule, from this. So this NADH is supplying the NADH to reduce oxaloacetate to malate. In return, the NAD that is being regenerated can be used by the glyceraldehyde 3-phosphate dehydrogenase enzyme to continue glycolysis. Now, once we form malate from this redox reaction, the malate has two fates. The first fate of malate is that it can be returned directly to the mitochondrial matrix, and it does so by the malate citrate transporter. This, of course, is an antiporter, and it balances the chemistry nicely because for every one citrate that comes out, one malate will return. So we have a nice balance of substrates and products. The other thing this is going to do is once the malate comes back into the matrix of the mitochondria, we are able to replenish oxaloacetate from the malate dehydrogenase enzyme in the matrix of the mitochondria. This will also deliver those NADH carrying electrons back into the mitochondria. So we pick up the NADH, which is generated by glycolysis, attach them to electrons to oxaloacetate to create malate. Malate brings those back in, and now we can unload those electrons onto NAD for NADH so we can process them through the electron transport chain. Because remember, there's no transporter for NADH on the inner mitochondrial membrane. Now the other fate of malate is to convert malate into pyruvate. This is going to generate NADPH. So in this particular step of malate, we are using the reduced potential of malate here that we picked up these electrons from NADH, and we're transferring those to NADPH to make NADPH. The reason for that is because NADPH, again, is our energy molecule for building for biosynthetic reactions. We are going to be using a lot of NADPH for fatty acid synthesis. Now recall the primary site for NADPH production is the pentose phosphate pathway. But the NADPH is of such vital need for fatty acid synthesis that we have a backup system to ensure high concentrations of NADPH being made in the fed state in the liver. Now the other thing that is being released from this reaction, malate recalls a 4-carbon molecule, pyruvate is a 3-carbon molecule. So we are losing CO2 in this reaction. The pyruvate, of course, in the cytoplasm follows the same fate as the pyruvate generated from glycolysis. it enters the TCA cycle through acetyl-CoA. Now, what controls this direction? Very important. The primary direction, of course, is going to be malate returning to the mitochondria, with citrate coming out by the transporter, by the antiporter. However, if there is a need for NADPH, let's say that there is a high use of NADPH while we are performing fatty acid synthesis, let's say that the pentose phosphate pathway can't keep up, we have this backup system here to make sure we have high levels of NADPH. When the NADPH levels begin to rise, that will inhibit the enzyme that performs this reaction. Thus, malate will be shunted into the mitochondria through the antiporter. The enzyme that performs this reaction, which is an oxidative decarboxylation reaction, is called the malic enzyme. Now let's turn our attention to the acetyl-CoA. The acetyl-CoA is only a portion of fatty acid synthesis. The other precursor for fatty acid synthesis is malonyl-CoA. We generate malonyl-CoA from acetyl-CoA by adding a CO2. This is a biotin cofactor dependent reaction. Biotin will assist in the transference of CO2 onto a molecule. And the enzyme that does this is acetyl-CoA carboxylase. Now, this particular enzyme has both intra-pathway regulation and inter-pathway regulation. The intra-pathway regulation is going to be simply a substrate feed-forward and a product feedback regulation. So as citrate becomes available in the cytoplasm, citrate will activate this enzyme. So that's a feed-forward. Citrate coming out indicate let's have fatty acid synthesis begin. Let's activate the enzyme, which is the rate-limiting step and entrance into the fatty acid synthesis pathway. Now, the last step in the product of fatty acid synthesis is palmitate. Palmitate is a C16:0. It's 16 carbons, and it is fully saturated. Hence, the 0 means no double bonds. This final product, as it builds up in concentration, will feed back and inhibit the acetyl-CoA carboxylase. And the reason for that is because of lipoprotein packaging. Lipids are dangerous in the hepatocyte because they can cause damage to the membranes if they're built up in too high a concentration. So we need to package the fatty acids into lipoprotein particles so that they can be transported rapidly from the hepatocyte into the blood. So as fat builds up, fatty acids build up, they will feed back and slow the fatty acid process by inhibiting the entrance of substrates into the fatty acid synthesis pathway. Now, because fatty acid synthesis is such an energy-expensive process, we're taking acetyl-CoAs, we're using NADPHs to construct these large energy-rich molecules. We only want to do this in a fed state. Now remember, fed state equates all the time with insulin activity. So as insulin levels rise in the circulation, insulin will have a positive effect, will activate acetyl-CoA carboxylase. The opposite to this is that when we go into a fasting state and our glucagon levels begin to rise, fasting state means that we need to conserve our energy. We are not going to be in a biosynthetic anabolic state. We're going to be in a catabolic state. So glucagon is going to want to make sure that we shut off fatty acid synthesis to conserve our precursors for energy. And so glucagon will inhibit the acetyl-CoA carboxylase. Now this is done, because these are hormonal effectors, this is done through other proteins, a higher regulatory mechanism, rather than binding directly to the enzyme and regulating it. So the insulin, in order to activate the acetyl-CoA carboxylase, will activate an enzyme called a phosphorylase. This is designed to remove phosphate groups that have been placed on acetyl-CoA carboxylase. Where did those phosphates come from? Glucagon is able to activate a kinase. And activation of the kinase places a phosphate group on the carboxylase enzyme and inhibits it. So again, we have two levels of regulation with acetyl-CoA carboxylase. We have the substrate feeding forward to activate the enzyme. We have the product of fatty acid synthesis feeding back to inhibit the enzyme, to slow it down. Then we have the hormonal control, which is insulin activating a phosphorylase to maintain the carboxylase in a dephosphorylated form, which is active. Counter to that, when we go into fasting, glucagon activates a kinase, which will then phosphorylate the enzyme acetyl-CoA carboxylase and shut the enzyme down. Now once we have our malonyl-CoA, we now have our two substrates necessary for fatty acid synthesis. We need malonyl-CoA, we need acetyl-CoA, and we need NADPH reducing power in order to put all these together.